Question number one, how many of you have hard copies of the book? All right, you guys need to, especially for this chapter on the in-step TD, look at the errata. So look at just errata on Sutton and Bardo. Because there are some errors. So in general, when you have a textbook, that's a good idea to do, but it's particularly important for this chapter. So like there's one equation that just says, replace it with the online version.
So the online illegal PDF is updated, right? Wait, is it illegal or legal? I can't really.
Oh, it is legal.
Oh, it's legal or illegal?
Legal.
That to me, both of them are good.
Yeah.
That one's updated?
I believe so. It wouldn't hurt to go look at the errata and see. I do know for certain that one of the equations, as I said, says look at the online version where that is correct. So likely that would mean the rest have been updated, but not 100% necessarily. So, yeah.
What is errata?
Errata means, what does errata mean? It's Latin.
Fixes.
Fixes, let's call it fixes. Yeah.
Is it like a section in the book, or
It's not in the book itself, it's online.
Oh.
Because the idea is if they could have done it in the book, they would have just done it.
I see.
And so,
That makes sense.
yeah. So, I guess in the past, probably some errata were done just as like an extra insert at the end. But for now, that's just all done online. So. All right. I wanted to go over one thing from section, is it 6? We're on chapter 6? 7.2. And that was on expected, in-step expected sarsa, as opposed to just end-step sarsa. So, right, we have the same idea where we are, let's say, going down in steps, but at the very end, instead of just taking this Q value, we go ahead and take the weighted sum here. See?
So if we're using like an epsilon greedy policy, do we, like, is the probability 1 minus epsilon for like the maximum and then split up for the...
So if we were using an epsilon greedy policy, then yeah, one of these would be almost 1.
And
And the rest would be, epsilon would be distributed among all of them. Yeah, so to be whatever those actual probabilities are that we're using for our policy. Okay. Does that distinction make sense? So what's happening, right, in expectation, as we go over all episodes, we're going to end up with the same value, right? We're going to basically end up with, occasionally we'll be going on the non-greedy path, and most of the time we'll be taking the greedy path. And so we'll get kind of by Monte Carlo in the regular sarsa, the same result that we get the expected. That we would have, I'm going to say we would expect. That can be confusing. So this would give us, in one fell swoop, really, a value that otherwise would require us multiple explorations to get to. So just like expected sarsa, in general, was better than sarsa. In-step expected sarsa would be better than in-step sarsa. On the other hand, in some ways, it doesn't matter all that much, because if we have discounting going on, right, this is just affecting the discounted reward for this Q step. So it may not really have much effect. All these immediate rewards might contribute to the return a lot more than this terminal value. On a different topic, let's talk about the stock market, okay? So stock market has been gyrating down, right, over the last week or something. How, if we've got some particular company, Apple, Walmart, any others, how can we value their stock? In fact, let's just forget about the stock itself, right? The stock is just a bunch of fractional shares of a company. How do we value a company? What's it worth?
It's how much it makes minus how much it pays, I guess. Maybe. Like its profit.
Okay, so profit. And how does that related to what it's worth? I mean, profit certainly matters on that.
The profit like increases or decreases its value, I guess.
I would agree. As the profit goes up, the value would go up. And as the profit goes down, the value would go down. Yes.
Isn't it like the number of stocks times the price per stock? Is it?
Okay, so the number of shares times the price per share, that's a simple formula for what's the total. So that's what the stock market is valuing that as. How, as like an investor, can we actually do a valuation? Like, what's it? Okay, go ahead.
Expected amount of future gains that you're going to get.
Okay, expected amount of future gains, we're going to say that?
Yes, guys.
Okay.
Also taking into account like the assets that the company holds, like
Okay.
physical assets.
So how about we look at the money you can get out, right? If I put in $1,000, or I buy a small business. Let's even forget Walmart. Let's say we're going to buy a local laundromat. Okay, we're buying this laundromat, all right? And we're paying $10,000 for the laundromat. We're going to expect to get money out of that laundromat, right? Now, are we expecting $10,000 like right away? We buy it one day, the next day we get $10,000, and every day from then out? If so, that's great. I want one of those. Right? That's like the golden goose laundromat. But instead, we will, let's say, invest some of that money, some dollars, and then we're going to get back. We'll say T. Some dollars T over time, right? So in our laundromat, we might get back next month $300, and the month after that, $350. And a year from now, we're getting maybe $400 because we've raised our rates or something. But we have a bunch of what's called like cash flows. The only reason you make an investment is you expect to get back some money, right? Otherwise, it's not much of an investment. If you invest in gold, what money do you get back?
When you sell the gold.
When you sell it, yeah. So when you sell it, you get it back, right? So that's still money you're getting back. But if you invested in gold and someone told you, here's your gold, no one will ever buy it from you, okay? Is it a good investment? I mean, maybe it's nice jewelry, but it's not a good investment, right? If you've never had any negative. So anyway, discounted cash flow analysis. Discounted cash flow analysis is one way of valuing a company. How much money is this going to generate the first year, the second year, the third year, the fourth year? And I'm going to discount those based on how long I have to wait to get the money, right? So I'm going to get, say, my returns in year one. And let's just not say, let's say cash in year one. Some discount rate times the cash in year two. Some, let's say, to the 9th in year 10. And we can just keep doing that, right? And that'll tell us our net value, our net present value for this stream of cash returns. Does that make sense? So this is like a rational way you can look and see. Now let's say your discount rate, right? if you have a choice between $1 today and $1 plus some amount in a year from now, what is that some amount for you? Is it you need to be 1% more, 5% more, 10% more, 20% more? You get to decide what this discount rate is for you. Let's say it's, I don't know, 3%, right? If the cash flows are growing greater than 3%, then you would have this amount today. You'd have something more than 3% a year from now, but you discount that down by 3%, but it's still more than this, right? Because basically if I say 1 over 1.03 times R2, this discounts it back to today. In exactly the same way that when we're doing discounted rewards with reinforcement learning, that if we have some R2, then we're discounting it back to today. But if R2 is equal to R1 and it's growing at 10%, so we're buying a company whose whose earnings are growing 10% a year, then this would be 1 times 1.03 times R1 times 1.10, right? So our present value of this is more than the present value today of cash in year 1. And in year 3, it'd be even more, more and more. And this would be an infinite sum. So if you have, I don't know, let's say you buy, someone says Apple stock, Apple, their earnings are going up 10% a year. What's that worth to buy? Well, if your discount rate is less than 10%, you should be willing to pay an infinite amount of money for that. There's some sort of a paradox there, because no one appears to be willing to pay an infinite amount of money for Apple. It's close to that, but not quite infinite.
Well, usually with this you have a specific time horizon. So retirement portfolios would be until 65, and anything earlier is probably shorter. Or you could do it until you have.
Okay, so a time horizon, here's why we have a time horizon. Trees don't grow to the sky, I think is the saying. Trees don't grow to the sky. Well, I mean, they grow towards the sky, but they don't grow infinitely to the sky, right? Companies do not grow infinitely large, right? Because if Apple grew at 10% a year forever, it would take the entire universe, right, to hold its money. That's not possible. So eventually, you have to stop this and say, this doesn't make sense. If I'm projecting this growth, why don't I just stop it at 10? Okay? And say, okay, here, just come up with a terminal value. What do I think it's going to be worth 10 years from now? Not using discounted cash flow analysis, but also kind of saying, let's just assume the growth stops. What's it worth? This is very much like a 10-step estimate of the value. So we have 10 rewards, we have discount factor, we're estimating those, what the rewards are, and then we're estimating some terminal value. That tells us what it's worth. So that's what's called like fundamental analysis of stocks. If it were a business, if I could own 100% of it, what would it be worth? And then I could divide by the number of shares and figure out what each share is worth. Okay. Let's do a quiz having nothing to do with the stock market. You have to pass them left and right. Okay, you guys can have one.
We don't need longer.
If you wanna give us one,
Yeah.
it's fine too.
You run out of
Is
coffee.
anyone missing any? Yep. give it one more minute. Okay, why don't you pass them on over to the right, please? So for the expected SARSA, our in-step return, right, is our immediate reward plus discounted rewards along the way, plus at our final step, our V bar here, right, where V would just be what's our estimate of the state. V bar is, given that we're in this state, what is our weighted, based on our probabilities of taking in particular actions, our weighted returns, right, or our weighted estimates. So this V bar is going to show up in some other places here. And basically, commonly what will happen for the V bar is we'll have estimates of Q, and so this just allows us to come up with an estimate. You know, this is what, of course, would be our best estimate for V, given that we have estimates for Qs. So far, everything we've done has been on policy, right? So in order to do off policy for n step, right? For one step, does it matter whether we're doing off policy or on policy? Which of the algorithms that we've seen so far can use on policy versus off policy, Justin? So the one step ones.
SARSA can use on step or on policy.
So let's say off, on, and this is one step. Okay, so SARSA
Is on policy.
Q learning,
Off policy.
off, and off is always a special case. Right? On is always a special case of off, right? So if we can do off, we can certainly always do on. And our other one we've looked at is
Just end step. End step.
in step is beyond this. The other one would be our expected SARSA.
Expected SARSA.
Right? I don't know why I do SARSA on uppercase, but I am. And that again can be on or off policy, right? So that the behavior policy is just sort of exploring various paths through our environment. But in each case, with this one step, we don't exactly care why it is we got there, or what policy led us to get there. Yeah.
And just to clarify, you can do off policy with SARSA if you use weighted or inverted sampling.
So let's actually think about this for a moment. So if we look at, let me see if I can get a darker pen. All right, so we have an S and A, we have our reward, we have S prime, we have our A prime, and right, our algorithms Q of SA plus equals alpha r plus, say again?
Gamma times kilo of S prime minus kilo of S.
And there, right? For our brackets?
No.
No.
It wouldn't make
Brackets
sense.
on the outside.
Okay, yes, well. Yes, because we have our target minus our current value, and this is the amount we want to update towards that, yes. Okay, so the problem here with the off versus on policy has to do with a particular action, right? So do we care off policy or on policy, the probability of taking this action with regard to this state right here? Action A in state S. Do we care what the probability is of B of A given S compared to pi of A given S? You were shaking your head, Nick?
No, we don't,
Because?
because you're always starting in that position anyway.
Yeah, it doesn't, we're trying to estimate what Q of SA is, and this is independent of what the probability of taking action A in step S. Action A in state S, right? Because the whole definition of Q is that we take what is the value after having taken this action and then staying on policy. Okay. So if we put some pi's in here, something like that, and that doesn't matter. But the problem is here, right? If our behavior policy is not pi, then it definitely matters what's the probability of actually taking this action, right? If this is an action that pi would never take, then this is not very useful. We've got to scale this by the sampling ratio. And in fact, we're going to do that right now. So for n step, we have to do this. Okay, for n step, we have to do this because of the fact that we're going to be taking these multiple steps. Right? So that is almost completely the case. We're going to look at a case where we don't have to, but in general, let's look at that. So what would we throw in here? That is, what factor would we put in here to adjust this?
The
Okay.
important sampling?
Yeah, we put in the importance sampling. So we put in sort of our row for this particular step. That is, what was the probability of taking A prime given pi? What was the probability of taking A given B? Divide the two and use that. So let's look at, let's say, state values. Okay, so if we look at let's look right now actually at defining our total reward. Okay, so we've got our total reward G. So this is our total discounted reward. From time step t, right, to t plus n. And we could define that, right, recursively as RT plus 1 plus our discount factor times basically going one step further. And we'd also need a base case. So something like G of the value of whatever that state is. I'm trying to figure out if I want a plus one here. Let's see. So what is the reward with sort of no time steps? Yeah, I believe that's correct. So if we want to look at V, from t to t plus n of, let's see how I want to make sure we're getting the terminology right. Actually, we have it up here, so let's make sure we get this right. So let's look at this. So at time t plus n, we've got some particular state. So we're trying to estimate the value of this state, and we're estimating it n time steps later, because we have to let the time steps go in order to do our backwards calculation, right? And then we can go ahead and multiply by our alpha, take our total reward, and subtract off our current estimate. Okay. This works fine on policy. If we want to do off policy, that's where we need to take into account that importance sampling ratio. And this is, of course, the same importance sampling ratio we were using earlier for off policy. So one thing we could do is just, so this is on policy. Off policy, we can add in another term, which is our sampling ratio. So taking each of the ratios for each time step and multiplying together, yes.
So are you able to do like weighted importance sampling and per decision importance sampling for this case as well?
We can do per decision importance sampling. The weighted importance sampling so I think the weighted importance sampling would only be useful when we're doing non-bootstrap method. With a bootstrap method, I don't think the weighted importance sampling would be valid. So, but the per decision we can definitely do, and we'll definitely get to. This one is clearly not per decision, right? Because per decision would say that the first reward would only be affected by the first ratio, and the second reward would only be affected by the first two ratios, and so on. But does this make sense? That would work? So let's look now, but it'll have high variance. Okay? Per decision is what gives us lower variance, while still having the same expected value. And then we're going to look at another approach of reducing the variance even more while keeping the same expectation. For SARSA, it's very similar. But I want you to note this difference. The rho has different bounds. Instead of saying rho from t, we say rho from t plus 1. Just in the same way, which got many of you on the exam, right, that we don't count the first row when doing importance sampling when we're doing the Monte Carlo. Because of the fact, when we have a Q, we don't care how we got here. We don't care why we're taking this action. We're just trying to say what is the value of taking this action and then following the fallacy. So here in the reward, we don't care about In this total reward, we don't care about discounting by that first factor of why did we take action A. What led us to take action A? Because we don't care about why you took the first action. We care about the next action. And we have to go one further. Because when we are doing Q estimates, right, we have one final Q value sort of hanging off the end that we need to be calculating. And so we need to be calculating the importance sampling ratio of that. Because in on policy, right, we're going from let's say we just have a two-step. Okay? So we have a kind of B, pi slash B here. And a pi slash B here, right? I want these pi slash B's to between my states and my actions, right? So this is from this state choosing this action, from this state choosing this action. In the case of off policy, let's label this differently. This is on policy V. I know it's off policy. It's off policy because I have a pi and a b. Okay, so off policy. It's a v because I'm starting and ending with open circles. Here, off policy, q. Try and start at the same place. So let's say here, and I want to use red. So here, I don't care about this pi comma b, because it doesn't matter, I'm just looking at this here. I do care about this pi over b, and I care about this further pi over b, because I've got this extra, this q term here that I'm going to be using. In this case, I use the v. I didn't even care about a future action. I didn't care about what future action was coming. Here, I am looking at this future action. I'm choosing this future action based on policy b, and so therefore, I need to take into account the difference between the likelihood of choosing in pi is choosing in b. So I have the same number of sampling ratio values, they're just offset by. Make sense? Make sure that it makes sense enough, either now or later, such that, like, if I asked you to compute this, you would get it differently for the v than you did for the q. You had a question, Sean?
What are the subscripts and the queues needed?
The subscripts of the queues are the time steps at which we are evaluating that. So if you think about this, this is state t, right, which we hit t time steps in, but we're actually evaluating q n steps after that, right? Because we hit this action, this state action pair, and then we've got to go all our n time steps before we can actually set. Does that make sense? Okay. Questions on this? All right, so now let's look at the per decision. Okay, so for the per decision, importance sampling, whose reason is to reduce variance. That is to keep the same expectation. That is that our Q is a good estimate of our actual Q, that is unbiased. So what we can do, right, this is just our recursive definition of G. This turns it recursive. Okay, so we're going to just look at it in the recursive form. But nothing's changed yet. And now, So we had a recursive form, we had our entire importance sampling ratio, this product of multiple individual ratios that was multiplied by a return. We're now going to define a new return. Okay, so the new return, the G tilde, actually takes into account the individual sampling ratio. So if we look at the first value, t to h, we're going to apply rho sub t to the first reward. And we apply it also to then the recursive. So the first sampling ratio is going to apply to all the rewards. The second sampling ratio is going to apply to the second reward and all following ones. And the last sampling ratio is going to only apply to the last reward. Sorry. Let me write that down since I said it wrong. So the first sampling ratio applies to, actually help me out here, McKenna, what does it apply to? So the first sampling ratio.
The first sampling ratio applies to all of the
I like it,
rewards.
all the rewards. And then C, the second sampling ratio. Where? There you are, okay.
The last one?
So let's just kind of work this out. So this is rho of t. We're interested in sort of rho of t plus 1,
Okay.
right? So if we look at g hat t plus 1 to h, that's going to be a rho of t plus 1. So therefore it's going to be, is it going to be the first reward?
No.
Is it going to be the second reward?
Yes.
Okay,
Everything from the second one?
yeah. I'm going to say from 2 on. And Varun, the nth ratio applies to
Everything from N on.
every reward from N on. Identical to how we were doing Monte Carlo, right? It's exactly the same values. So what we're doing is capturing all of the importance sampling ratio in the return, in our G hat, and removing it out of our calculation of the state value. Questions on that?
So
Shannon.
like ratios that are being applied are only like n steps that we're looking at.
It is only the end steps. So Monte Carlo, right, it was from here all the way to the end. And here it's just the end steps that we can see into the future. What happens if we get a ratio of 0 somewhere, Kaki?
The whole thing goes to 0.
Does the whole thing go to 0?
Or from that point.
Yeah, from that point on, exactly. When we looked at the previous one, right, when we looked at where we're converting from, the whole thing would go to 0, right? Because if any one term in here is 0, then the whole thing would be 0. So that would take the entire reward I'm just looking here. So, yeah, this is unfortunate. They would get really mad at me if I did this. We need to cross out this r sub t plus 1. So, I apologize for that. Because it's already captured in the total reward in G, right? Shouldn't be there. Let me just make a quick change.
capture that.
Oh, no, I just didn't what he was saying.
Yeah, it's just fine. Whoop. Okay, now what has happened? Yeah, that is correct. So all the returns are captured in here. And the RT plus 1, that is the very first reward, will get just the first ratio applied to it.
And, but this is using the value, this is using the state value function. If we use Q instead, then we use RT plus 1 for that.
That's a good point. So if we were using the action value, then we don't want RT plus 1 to be Rhodes. Right? And so I have an error in the bottom. We'll deal with that in just a moment. But the difference is we would basically pull the row over here so that the R stays out of it. Okay. So that we're delayed with that row. Okay, so that was a good question. All right, so going back. So here we are, right? We have got our per decision importance sampling. And this actually works. This is equivalent to what we were doing in Monte Carlo. But we can do even better. Okay? I want to reiterate, why do we do per decision importance sampling? Does it change the expectation of the value? So this is, let's call it simple importance sampling. No, that's not what we call it. We call it ordinary importance sampling. And then we have per decision. Importance sampling. And so the question is, what happens to the expectation? Is this biased? Alfredo biased? Alfredo just walked out, didn't he? He knew. So he comes back, remind me, I'll put him back at the front of the queue. Ali, is the expectation here biased or unbiased with ordinary importance sampling? Unbiased, that's right. The multiplying by the sampling ratio is what causes it to be unbiased. Because we want, that's what we want, right? And the multiplication by the sampling ratio switches from an expectation with respect to B to an expectation with respect to pi. So unbiased. All right, what about the per decision importance sampling arc?
Unbiased.
Because?
It doesn't take into account the whole trajectory.
And I would disagree. Here's why. The only thing that the per decision does is say, the equivalent of like the first reward, we only use the first ratio. Do we think the first reward should be affected by subsequent decisions that happen? No. And same for the second. It should be affected by the first and the second. How do we get here, but not where am I going from here on out? So this one is also unbiased. Okay? But if I look at the variance, this is high, and this is low. Lower. Give me an example of how it would be lower here.
I guess, I don't know, I'm trying to figure out how the expectation.
So let's look at the very last action. You've got n steps, And the first n minus 1, let's just say actually it's exactly the behavior policy and the target policy are identical. So the ratios are 1. The ratios are what? If the target and the behavior are the same.
1.
Yeah, so we got 1, 1, 1, 1, 1, and the very last action, the target policy says I would never do that. So the behavior policy takes an action, the target policy says I wouldn't do that. So if we multiply, so therefore that ratio is 0. So we've got a bunch of 1s and then a 0. The ordinary way says, well, we take the product of all those, that's 0, and we're going to go ahead and say the entire thing is 0. Okay? So I'm going to just ignore the first reward, the second reward, the third reward, all the way to the n minus first reward. The per decision importance sampling says, fine, that last reward, we just can't count, right? But all the previous rewards, we can go ahead and count. And therefore, we're going to get a tighter estimate. And the tighter is what gives us this lower variance. Does that make sense? Any questions on that? All right, so we want to fill in something that continues to be unbiased, and that is even lower. Okay? Sounds good, right? We're not going to get a column that's 0. That'd be nice. So let's look at what that is. And now we get this weird naming, which is called control variance. So here's the idea. You're trying to estimate, right? An estimator basically is estimating the mean of a random variable, right? The expected value of a random variable. So you want some e of x. We can come up with an x star which has the same expected value. Or rather, I mean, we can. And so we're going to look at how we can design an x star that is like x, but will end up having a lower variance. So if we define x star to be x plus a constant times so let's just look at this. I'm going to put the random variables in green. Okay? So x is a random variable. C is not a random variable. C is a constant, right? So we call it C. And now let's go ahead and take the expectation of some other variable, y. What the heck? So we have now a new random variable, but it's a random variable for which we know its expected value. Okay? So we have a y, we know its expected value. And somehow our claim is x star and x share an expected value. Almost gives a reason for that. Okay? Tell me about expected value of, so just a plus b. That's equal to
The sum of
expected value of A plus the expected value of B. If I change these to times, does this work?
it only for independent.
Yeah. If they're totally independent random variables, then yes. But if they're not independent, no. So this is what? Linearity of expectation? Because the word is the word for this. So linearity of expectation. So this says that the expectation of x star equals, and I'm going to get rid of the greens and blues because it's too much work, it turns out, equals the expectation of x plus c, expectation of y minus y. Yes? Just take an expectation. We have linearity of expectation, which means this is expectation of x plus expectation of, and c is a constant. I can pull the constant out, okay? So let me just do that right now. C times expectation of y minus y. And I can sneak this in right here. Actually, I'll put it below. So we're going right to here, which is equal to the expectation of x plus c times, well, linearity of expectation means we can do this again, right? This is a difference, we can do that. So expectation of y minus expectation of y. All this times c. Josh, expectation of y. No, not quite. Actually, what kind of thing is expectation of y? We know y is a random variable, right? Is expectation of y a random variable?
No,
It's a number. The expectation of a number is
a constant.
what constant? What's the expectation of 3?
Just 3.
Yep, I agree. No matter what I do randomly, 3 gives me 3. And so therefore, expectation of y is a constant. And so if I take the expectation of that, it remains whatever that constant is. So this is c times expectation of y. Makes sense, right? Because expectation of any constant equals that constant itself. Minus expectation of y and this is just 0. So, control variance. Say, if you've got a variable, it's a random variable, whose mean you know, you can add in the random variable minus the mean minus the random variable. Multiply by a constant if you want. And you'll end up with the same expectation of your original. So if you're lucky, this will reduce the variance. In fact, there's a formula, depending on the covariance of these things, to figure out what's the exact best constant to be using here to reduce the overall variance. Because these two will not have the same variance. They'll have the same expectation, but not the same variance. So what we're adding to this chart is per decision with control variance. And we're going to get even lower.
So for that formula there, like it looks like it's basically like c times a variable with 0 average, because expected value of y minus y is basically like a variable centered at 0.
Yeah, that's a good way to look at it. We've got y, and what we're doing is translating it so that its expected value is 0. That's
So my
another way.
understanding is that like, if you have like two variables with different variance added, like the variance usually there's a formula that like they only add together, so why would it decrease?
So if you have the variance of a plus b, you don't just sum together the variance of a and the variance of b. Right? This is the case where I do not remember the formula and have to bring it out, but it certainly includes the covariance and also includes c in there, such that I believe what ends up is the minimum variance we would get here is, I believe, the covariance of x and y divided by the variance of y. I believe is what we end up with, but I'd have to refresh myself.
How do you choose Y and C? So that like you get
Yeah.
one.
So C you choose based on, I think it's negative the covariance of the two divided by the variance of y. Okay. So in our case, we're not going to see how I want to describe this. I don't want us to look at how do we choose C to minimize this. I just want to look at, okay, this makes sense that it's not going to change the mean. And let's look at the change that we make to per decision importance sampling, verify that we're going to make a change that doesn't change the mean. And then we'll just look at some examples kind of to see why it seems reasonable that it's reducing the variance. Okay. Other questions right now? All right. So here's what we're going to do. I don't need this chart anymore. This is where we're going. Okay? We're in this column here. Here's where we're going. So we have g hat. Remember this guy? Right, this is for our state value. We multiply our single ratio by our reward, and then gamma, and then the remaining reward, or remaining return. We are going to redefine g, so instead of g tilde, we now have g hat. So we've looked today at hats and tildes and bars. I guess we could do umlauts next, if we want. So we have this value, and we're going to add this on. What's the name of this added on thing? Jake? What kind of a thing are we adding on? That's the control variable. Okay? So we are expecting it's of the form C times expected value of some random variable minus a random variable. What must C be in this case then? Yeah, it looks like C is 1, right? Expected value of a random variable minus a random variable. Right? You need something like expected value of y minus y. Well, I'm going to say v of st. I'm just ignoring the subscripts. Too much to write. And that's our expected value. And y is going to be rho sub t v of st. Does this make any sense? So, let's look at this guy. So, hold on just a second. Let me check one thing. I just want to make sure that I don't have a defect there now. So this is a sort of expected value of v of s of t. It's our approximate, right? It's not, it is an approximation to that. It's an estimate of our actual value. And then we also have a particular sample that we got based on our importance sampling ratio. That is based on the episode that we've got. We had a particular estimate for V, okay? And we got there by taking some particular actions chosen according to B. And then we know that if we didn't adjust, we would have a biased estimator, right? That if we looked at this over time, we'd be ending up estimating towards B's value rather than pi's value. Yes.
So given ST is V deterministic or not?
Given
ST, like does V always return the same value or not?
V does return the same value. Our pi's are not. Sorry, our rows are not. Where did our rows come from? Our rows came from two forms of randomness. Our environment, right? As we're taking particular actions, what's the particular sequence of states and words we got? And also our B policy, our behavior policy, right? So depending on what behavior policy is going to tell us kind of how we got here, how we got to S of t. So this is like one draw. If you think kind of a Monte Carlo, we're going to go ahead and see what happens running through these n state action traversals. We go ahead and correct it to be unbiased so that we're actually estimating for the pi policy rather than for the B policy. Okay. So kind of in the long run, knowing that this is only an approximation, but in the long run we'd expect that the expectation of these two is going to end up as a 0. If we rewrite it, we get something like this, which kind of looks like a weighted sum, right? We're going to say g hat is equal rho t times this plus 1 minus rho t times this. Now, it's not quite a normal weighted sum, because normally you would think this would be between 0 and 1, and this would be between 0 and 1, but rho sub t becomes between 0 and infinity. Right? So let's just look at what happens when rho is 0. If rho is 0, what we used to say is, then our estimate is 0, right? From then on, right? If you had non-zeros before that, that's okay. But from this point on, a 0 means everything else is 0. And now we're saying what instead? If rho sub t is 0, this term is 0, this is a 1, we're saying our estimate is just the estimate of the state we're in. which kind of makes more sense than saying our estimate is 0. So we got to a state. The state has this value we've given it, we currently estimate to be 1,000. All right? And now all of a sudden the behavior policy takes a right turn and goes off on some behavior, some action we would never do. Do you think our best estimate is 0 or 1,000? It's probably 1,000, right? And that's what this is doing. Right? That's kind of an explanation of that. Okay. If, on the other hand, rho sub t is very large, then we're really highly weighting this, right? Super high weighting it. What's going to happen to this? This one's going to be negative, right? So all of a sudden we'd say, hold it, let's put some brakes on this super weighting. We're going to put some brakes based on what our current estimate is. So it's going to tend to remove the extremes, or slow down, pull in those extremes. Now, pulling in those extremes is exactly lowering the variance, right? And the nice part about this is we're lowering the extremes, but we're maintaining the same mean. That's precision importance sampling with control variance.
Just for clarification, the expectation there, that's under pi, right?
This one?
Not the.
Oh, this one?
Okay. Yeah.
So let's, unless there are any other questions, I want to show you a method where we can do this n-step off policy without importance sampling. So questions about the importance sampling. The control variate is different when we're working with action values rather than state values. But the same idea holds, that we're just basically adding this term, one of which is the expected value of our variable, and the other is variable. And so, in expectation, those go to 0. Which we think it's just in the long term, it goes to 0. So did you have a question else?
This is still for n-step TD.
This is still in step TD. This is basically 7.4. But the real important thing here, I'd say, is understand this idea of control variance. So in the general case where I talked about, why does this work? And then, why did we give those? These are just, I don't have a good reason for why we chose this variable. We had it. Yes?
Also, is per decision always on policy? Or you can also do off policy?
So per decision doesn't make sense for on policy.
Right.
Because all of your importance ratios are 1. And so therefore, it doesn't matter whether you multiply 1, 1, or in ones, or how you multiply it. So the per decision is always going to be for off policy. Other questions? Let me just give you the diagram, and we will talk about it some more on Wednesday. So this is like an expected sarsa, but blown up from the bottom of the tree all the way up. Okay, this is called tree backup. So the idea is we're in a state, we take an action, but we still take into account what are the other possible actions we could have chosen with what probabilities. Okay. We have a behavior that chooses this action, but that's not the policy that we're evaluating. And then we get to this state, and we say, okay, what does the behavior say to do? Okay, let's add up all the rest of them with the chance of having gotten there. which is basically what's the chance under the policy pi of getting here times the probability of getting here. So if we look basically at any leaf, we can figure out what's the probability of getting there. Just look at our policy pi and say, what's the probability of following these actions? We'll weight that reward appropriately. And we do that for every one of our leaves. Just say, what is the probability of having gotten to this leaf based on our policy pi? We'll talk more about that on Wednesday. Any questions? Program assignment tomorrow night?
Yeah.
Is that right? I'll be in the cafe.